Okay, let's start. Good morning, everyone. Yesterday we had mainly the topic of the design flow. I always, at the beginning of the lecture, do some short recap so that we reflect a little bit and you have the chance to ask questions to the day before. So this was our design flow. Just take this one here. So we have, from a designer's perspective, 4 main steps, which are, after some specifications, some architectural design, functional design, circuit design, and physical design. That is mainly where we, as electrical engineers, work on. So for a quick recap, what would you do in different design steps? So what is the task for, let's start with architectural design. Any idea? Proposals? What happens in architectural design? What architectural design actually is about? Yes, so we break down the design into modules, submodules, sub-submodules, so that we have partitioned it into individual blocks that we can well implement. In addition, we have to define the interfaces between the different building blocks. Then, if this is done, we go to the functional design. What is done there? What kind of level of abstraction are we talking about here? So the question is, on architectural level, we talk about an algorithm, we break it down into blocks. Now we go to a functional design, logic design. What is the abstraction level we are talking about here? So how do we describe on that level our functionality? The frequency of the circuit is some specification rather, that comes typically in, or that we can also analyze at the end. But for functional design, so is it clear what I mean by abstraction layer or level? So abstraction layer level means how do we actually describe on this level our circuit? Because effectively all we want to do at the end is we want to have here some chip, right? All what we do before is modeling of what we want to have at the end, right? So we have the different abstraction levels of our chip, different levels of description, which from the effectively physical device go higher and higher. So we have here specific level, which is close already to the physical world. This is further away, further away, further away, and at the end, on the very top, we are at this block level where we start our design, right? So abstraction level effectively is about how to describe on this level our circuit. Why do we do this? These different levels, because on a higher level, it's easier to describe complex systems, right? So it's much easier to describe our circuit with blocks, where we say, okay, this block has this functionality, this block has this functionality, than to start with describing each individual transistor, right? That's the reason why we do this. So maybe I give the answer for this one, and you can try for the next one. So this one here, effectively the modeling is done with RTL, so the abstraction level is a behavioral description or RTL description. So just the transfer level description. We do some coding at the end. Okay? If we now go further into this circuit design, what are we talking about here? Gate level and transistor level. So we translate, usually with some tools, what we have programmed into some form of a netlist, gate level netlist or transistor level netlist. If we talk about physical design, what is this about? P-diffusion and diffusion is, let's say, part of what comes out there. So we define where P-diffusion and the layout, exactly. So when we talk about the physical design, then we usually talk about place and route, layout of the design, routing of the design. Huh? Okay. And then the rest is verification, testing, and taping the chip and sending it to the fab, and then some, mostly material science guys, also some engineers work on the fabrication of the chip, and then we get it back and do some post-fabrication processing. So packaging the chip, putting the testing the chip, stuff like that. Okay, good. That were the different design steps we talked yesterday about. That were more examples. Yes. Then we had this the V diagram. What is this about? Or what does this describe actually? Yes. So it describes actually how the design flow works in a specific model. There are different models. This is one that is very common. That is why I have it here. So you start, actually these are the steps we had before architectural design. They have the split into system design, subsystem design, and so on. So what we had was more or less this part as architectural design. Then we have this component design, and implementation is more or less what we say, we type our RTL code. And then it goes up validation. So we have also physical design, of course, included. And for each step, we have a corresponding validation step. So it should say, okay, we have at the end, we have everything what is implemented should also be verified. Okay, that I can skip for today. Yes. Then we talked a little bit about different simulation types. So yes, we have functional and timing simulation. We have the different implementation steps. So behavioral, post-synthesis, post-implementation. If I look into this table, obviously there is no behavioral level timing simulation. Why not? Any idea why there is no behavioral timing simulation here? Did I just forget to tick the box, or kind of, I would say? So where does the timing info, or what does timing mean? Where does timing information come from? A clock is one component of the timing, but let's say, just as a rough example, you have some circuit, some logic. Let's make another flip-flop here, and then here, an AND maybe, and let's maybe one other path I need to have something a little bit more complex. Then I can hopefully give a bit more meaningful examples. And we take maybe here. So just a random circuit that came into my mind. No idea if this makes any logical sense. So this is what we implement. I can write a behavioral description of this. Agree? So that would be, we have some registers, and we have this register is set if this is set and this is set. This register is set if this is set or this is not set. That's pretty simple. Well, Maybe we don't know the syntax because we did not learn about this, but we can, if we know the syntax, we can just code it, right? So, now we talked about timing. I tell you, this here is my clock. Can you tell me the frequency of this? No. Why not? It's not specified? Yes. What are you missing? Yes, I could give you the frequency, then it gets simple. Huh? If I don't know the frequency, I say don't care. Tell me how fast I can get. You still don't know, right? You cannot know. So what information is missing? No, we have only one time used. Huh? Exactly. So we need the time it takes for the signal to propagate for each component. So what means each component? We need here for this inverter some t. We need here some time. We need here some time. Are we done? No. We need for the registers also timings, yes. So we need here something like, this one is not so, here we need actually t, q to c, so clock to q. Yeah. So this is q, this is clock, the time it takes for that. Yeah. That is the important time information for us. And we need here t setup and t hold, right? Okay. What else? Oh, I did not get the last word, sorry. The holding time we have here, the t hold, okay? That we have? Well, what is missing is actually, we start with what we have. What we have is actually we have selected the components, yeah? And we have a delay for each component. We have a delay for the registers, we have fully described, for the OR gate, inverter, for the AND gate. This is what we have available for the synthesis. So we synthesized our circuit. We have a gate level netlist. We have a transistor level netlist. We know which components from our gate library we have selected. And this gives the timing for these components. Now, where we are not yet is effectively the information for here. So, in practice, we have here, for each of these wires, we have some capacitance, right? Simplified. So, since each of these wires has a capacitance, each of these wires has a delay. So if we want to consider also these wire delays, we need the information how long the wires are, what the specific capacity is at the end. And for this, we need to place and route our circuit. And that is why we have a better model than here, right? So we can have a rough estimate for this delay here, but we can only give a worst case or some guess, some educated guess from the fab that is included in some synthesis, but no precise timings. Usually what is done is that there is some worst case estimate. So that usually your timing tends to become better at the implementation, but not necessarily. So this information has to be included if we want to have the complete picture of our timing, and only if we have what the gate delays are and what the plus registers, so the component delays, let's say, plus the wiring delays. Only then we have a good estimate of the final timing. For the behavioral simulation, so to come back to my original question, why here is a gap. For the behavioral simulation, we start effectively with what I gave you at the beginning, right? I gave you no information what the delay of the gates is. I gave you no information what the delay of the wires is, so you cannot estimate what the frequency is, the maximum frequency. Okay? Good. Then we talked about setup hold times. I add here maybe some buffer to make it a little bit more interesting. Okay, now we want to know, we have here a specified clock. Yeah? Our customer told us, I want you to run the system on, let's say, 100 megahertz, yeah? So which is 10 nanoseconds, yeah? As a period length. What do you need to do in order to verify if your circuit can run on this 10 nanosecond frequency? Actually, the frequency doesn't really matter. Yes. So what should be what should we compare? So we have two delays that we need to compare. The one, probably simpler one, is the one from the clock. So we start effectively at some common node, huh? And get a timing here. I write it capital T clock, huh? Not to mix up with the period length of the clocks, but the clock path length. Huh? So usually the circuit is, or the timing of these buffers is not perfectly equal on each chip. Huh? So if you manufacture the same chip 3 times, the precise timing will be 3 times different. If you heat up the chip, if you change the supply voltage a little bit, just variations that you have in your supply, the chip has some fluctuations. Huh? So the timing is not one fixed value, but it's usually somewhere in a range. What you do in practice to cover this is that you have a maximum and a minimum delay. Huh? So we may have here T clock max and a T clock min, right? Good. Now we want to compare this, as you said, with the data path. Huh? Which one do we take? That one? So this is our clock path, right? And we want to compare with one of the data paths, with the burst, well, depending on which one we want. So what do we need to know? Well, we need to know what is our longest and shortest path, right? So for that, of course, we would need some timing information. Usually, without giving now precise number, because we'll do some computations like this in the exercise. But usually, an OR gate is slower than an AND gate, and if we have here an inverter, then we have here an additional gate. So the most critical path is most likely, including clock to Q, the one which goes here, right? That's most likely the most critical path. That is, we call it TD max, right? Something unclear? Because just interrupt me, just that I don't make a mistake somewhere. Seems okay? Okay, good. Just if something is unclear, then sometimes there is just some mistake, some typo what I overlooked there. So this is the maximum delay we have. Following the same logic, the AND is most likely faster than the OR, so there is a path, probably assuming this delay is equal for all, which is somewhere here, which we call TD minimum. So we want to compare this to passes, and if we want to know if this here, if this clock frequency can be reached, what do we have to ensure?
Maximum.
So effectively, the longest critical path, well, maybe I should make it a little bit more concrete, then it becomes more clear. Good. We have here, each of these gates has some timing. So maybe these times are just random, yeah, but the relation should be somehow okay. So we have maybe a t end where we say this is somewhere between, don't know, let's say 1 nanosecond and 1.2 nanoseconds. We have a T inverter where we say this is somewhere between, let's say, 0.8 nanoseconds and maybe 0.9 nanoseconds. Yeah? It's faster because there are less transistors which have to switch. Yeah. The OR is a little bit slower usually than the AND, so we have maybe something between 1 nanosecond, smaller T OR, smaller, let's say 1.3 nanoseconds. Yeah? Just to have some numbers in mind. Okay. Now, the shortest critical path, in this circuit is given, well, if we go through this, I just neglect the wires here. Yeah? Because otherwise we do just additional computations, we add something up, but we can neglect here. So, the path through this here, through the inverter, through the OR, takes, in the worst case, 0.9 plus 1.3, so 2.1. The path through the OR gate takes, in the worst case, 1.3. The path through the AND gate takes, in the worst case, 1.2. So the slowest path is obviously this one. Huh? The shortest path, we go for the minimum. Huh? So for the minimum, we say the fastest, or the path here is 0.8 plus 1 is 1.8 plus 1.1. Yeah? Is 1.9. The path here through the OR is 1.1. The path through the AND is 1 nanosecond. Yeah? So the shortest path is this one. Okay. Most of the time in the exercise and so we will not have this range. We just have one fixed value for each delay. Yeah? But it's effectively, if you want to really do it in a circuit simulation, then you will end up with these ranges, these margins where each delay is inside.
So both are critical path, one is the longer push.
Yes, I've drawn both of them because of reasons. Yeah? Because the first step now is, or the question now is, we have a longest path, we have a shortest path, we have a clock path, maximum, minimum. Yeah? What do we have to compare? We wanted, the original task was to find out if we can meet this clock frequency. Right? So what do we have to compare? TD max should be larger, smaller, equal, smaller. Which clock? Maximum or minimum? Minimum. Is this all? We do some cheat sheet, this one here. So, what do we compare? I had here TCS, that's not precisely what we have here, yeah? Take care. TCS minus TDS. TCS was defined the minimum delay of the clock, yeah? Minus the setup. So, we should effectively here minus T setup, right? Here we have this delays. Here we lack effectively the clock period. Yeah? So we have here plus, let's call this here, I write this as T0, yeah? Equals 10 nanoseconds. Yeah? That's maybe more better to have. Huh? So then let me quickly check that we did it the right way around. Yes. Huh? So this is effectively what we need to check to ensure that we can run the circuit on that frequency. Why? Because we need to ensure that the signal that is sent here with a rising clock edge arrives here early enough before the next clock edge that goes this path, rising clock edge. Okay? This is effectively what we check if we do in our physical design, so, or also in our synthesized design already. If we do a timing analysis, then we do effectively the tool searches the critical path and does this check. And then for each pass, it can compute some difference here. So it does not do the comparison directly. It just computes this difference here and gives you out some slack. If it's positive, then you're lucky, then you met the criteria. You may even have some room for optimization to make your design, let's say, more area optimal or something like this, and making it a little bit slower. If you have a negative value here, then, well, bad luck. You need to improve. Okay, let's assume for our case here that works. I don't know exactly. I did not compute the numbers. I even did not give a setup time, so just assume this works. Are we fine if we have no negative setup slack? Or what is missing? This is already included here. That's here. The T buffer is actually in the screen pass included. So that the timing for the setup time is fine. What is missing? No. So let's look onto the next slide here. What is missing actually is hold time. So what does hold time mean? Hold time means whatever we want to send here, or whenever here a clock arrives, the data at the output should not be overwritten before they are output. So that means the data path here needs to be slower than the clock path. Okay? So this is also why I had here this TD min. Because what we now have to compare is the fastest data path with the slowest clock path, right? So in our case now, we want that TD min is larger than T clock min, right? Not complete yet. So we have, this is our equation, so TD minus TCA, so TD is larger than the clock. We need to take the maximum clock, that should not be min, but max, sorry. There we take the minimum, so that's already there. What is missing is the hold time. Because even after the signal, even after the clock arrived here, our signal should stay stable for a while. So we have to add here on the clock side plus T hold, right? Again, this is not what the tool computes. The tool just computes the difference here. And it's defined so that if you have a negative slack, it's bad. Just to have the same intuition as before. It's just a definition how this, what is good and what is bad. And reverse negative slack. If this is positive, then you can have actually ensured that you have no hold time violation. Most of the time, the hold times in a circuit are pretty okay. The reason is that you design your clock tree in a way so that your clock ideally arrives on all the flip-flops at exactly the same time. That's just how you design the clock tree. And your data path has some delay, so it is inherently usually given that you have no hold time violation. Where it can happen, for instance, is in a shift register. So, is it obvious what a shift register means? So it's just a series of flip-flops, right? So you have effectively, shift register means you have a structure like this. Purpose of such a register is, for instance, let's say, maybe I do another one. So very common used for this is you have a sequential, so serial input, where one bit after the other comes in. And with each clock cycle, you shift this in, and at the end, you have here some parallel structure out, where you have 8-bit in parallel then output. So actually, parallelization, deserializer. Yeah? So such a structure, of course, you have here no logic in between. Yeah? Because it's just a shift. It goes from here to here. What logic should be there? For such a structure, there is a certain chance that you have a hold time violation. So for such a structure, because you have no logic here in between, you have a certain chance that your shortest critical path, your shortest path, is smaller than or faster than the clock. Because there is no logic in between. So it's only the wire. Yes. If you have such a problem, what can you do? So you have this structure here, and you have a hold time problem. How can I increase it? Yes, that's not particularly increasing the hold time, but it's increasing the data path length. So you can actually add here some buffer, and here, and here, if this is needed. The price to pay is your circuit gets larger. Significantly larger, because before you had no logic, now you have logic. So, you could theoretically, what you said, also try to increase the hold time. How can this be? Well, you have maybe different flip-flops in your library with different hold times. And you can take another one. Might be. Otherwise, you have to go to your analog mixed signal designer and ask if they can do it. But usually on a digital design level, you just add a buffer there. Okay, if we would have a setup time violation, what can we do there? So we can again go to our analog designer and ask for help, but that's maybe not the best choice. So we can try to shorten the data path. How can we do this? Minimize the logic gates. We are already quite on the limit. So you're right, we can try to do this. But in our case now, we have an AND gate. Here we have an OR gate and inverter. Let's say we have no integrated OR gate with an inverter in between, so we have already chosen the optimal gates that we have available. We can try to decrease the clock. Okay, so let's say we do not want to go to our analog designer and ask for help, so we cannot change the gate. Our customer says, no, we are not allowed to change clock. You're right that we can do this potentially, but our specification tells we have to run at this at minimum, and our customer does not allow us to go below. Yes. So we can add registers, add flip-flops in between. Right? To be synchronous, again, we have to add them maybe, well, the only place we can reasonably add one would be here, right? So maybe I take the black color here. So the only point where we could reasonably add one is actually here, right? Now by adding this register, we also changed our logic functionality. So we have to add a register here, and we have to add a register, don't know, maybe here. Yeah? Then at the same clock cycle, we have here the same logical result. Right? We now take for the same logic functionality 2 clock cycles. We now need for the same logic functionality 2 clock cycles, right? Because we first need to process here, and then we need to process here. But we can run at a higher frequency that is determined only by the OR gate. Right? Now we are maybe back at the problem that here no buffer is inside. So we may have to add a buffer. Yeah? But that depends on really on the wiring and so on. So this is how we would approach effectively if you have really these setup and hold time problems. The first things to check, as you did, is can we improve our logic? Can we try to reduce our frequency? Because then we can just keep our circuit as is and everybody's happy. If not, we have to take these additional registers, but additional registers means significantly more area. And that was the other performance criteria we had yesterday. That was actually, we usually want to minimize the area because area means cost. Okay? Where you mean here? If we would add it here, well, what would we win? So this register here allows us to have one clock cycle to process the inversion and one clock cycle to process the OR. Right? If we would add it afterwards here, what would we win? Let's say we skip them, then we have the critical path now from here to the register here. Right? If we have an additional one, well, we have one delay for this OR still as before, and the delay of this wire here, so we will not win anything. Okay, good. Questions to this? Good. Then, yes, maybe this we can also make here. If we add here the registers, that decreases our critical path. So it increases our frequency. That was this one here. What does it mean for our latency? So adding here this register, how does this change the latency? Latency we defined here as the number of clock cycles to perform an operation. So the logic operation before adding these black registers was 1 clock cycle, right? After adding it, the same operation takes 1, 2 clock cycles. So latency increases. Can we reach, with adding these black registers, the same throughput? So we said, okay, we have the frequency, one thing. We have the latency that goes down. So frequency maybe go up, latency goes down. What does this change mean for our throughput at the end? Can we keep it the same? Can we increase this? Do we decrease it? We decrease. Why? It's more clock cycles, that's correct. The frequency goes up because we have reduced the path lengths. It may be that if you do it like that, because you cannot just double most likely frequency, that your throughput goes down. If you if this allows you to double more or less the frequency, then it's the same. More will not happen. I claim that even if your frequency is roughly the same, only a little bit faster maybe. So let's say instead of, before we had maybe 10 nanoseconds, now we can run at the 11 nanoseconds, now we can run at the 10, but we have 2 clock cycles. Even in this situation, I claim you can improve the throughput. How can this be? Yeah, but we have, let's say we have, so before, roughly spoken, we say throughput is 3 bits processed to 2 bits. 1 clock cycle is the time, is the number of clock cycles that then we have to multiply by, let's say, 11 nanoseconds. That was what we had before. Now we have 2 clock cycles at 10 nanoseconds, what we have now. So now we are at 20 nanoseconds. Before we were at 11, which should mean the throughput goes down, right? What you initially proposed. Still, I claim we can improve it. Under which condition? So, if we process more data, then we can increase the throughput. Why? Because we can do a pipelining approach. Yeah? We can, in the first step, in the first clock cycle, we process the data from here to here. In the second clock cycle, we process the same data word from here to here, and the next we already prepare. Yeah? So the latency of the overall thing is the same, but every clock cycle, now with 10 nanoseconds, one result drops out. So if we do enough processing steps, then we see effectively the throughput of 10 nanoseconds, one clock cycle, instead of before 11 nanoseconds, also one clock cycle. Okay, I think that was all what we had yesterday. So, 2 words I want to add from the slide set from yesterday. So, the first one is what is also important, but I do not go into detail in this lecture, is power energy, obviously. There are 2 components. One is static power, the other one is dynamic power. Static power means, in theory, if your inverter gate, let's say, is in a stable state, so either 1 or 0 at the output, you have no current flowing from drain from VDD to ground. In practice, you have some leakage currents. They go into a little bit into the bulk, they go still through the channel, whatsoever. So you have effectively no completely, no complete off of your current. Meaning you have still here some current from VDD to ground, either as I said, to the bulk or somewhere else, and that is called static current. This is, in old technologies, is more or less negligible. In modern technologies, so some 20 nanometers below, there the contribution of the static power becomes also significant. What you can do to avoid this, without again going into details, is to build things like power islands and to switch off a part of your circuit completely. That can be done. Yes. Then there are some, let's say this. The other component, most relevant in old technologies, still relevant in new technologies, is dynamic power. Why do we have dynamic power? Well, if we switch here from low to high, or from high to low, these transistors here start to open. So to start to be conducting, both of them. The one starts to be non-conducting, the other one starts to be conducting. That causes that for a short time you may have a direct current from VDD to ground. That is one component of the dynamic power. The second component of dynamic power is, even if there would not be a current directly, you have always a capacitive load here at the output. This is, on the one side, the wiring you have, on the other side, the next gate where you have to drive the input. So the next gate here is effectively a capacitance between this gate terminal and the bulk, right? So you have to charge and discharge this specific capacity here, and discharging means you have some current flowing in here, means you have some dynamic power consumption, just by switching this capacitance. This is why this is proportional to the toggling. What you can do against this are things like frequency voltage scaling, meaning that you switch off No, meaning that you slow down your circuit. Yeah? So you run it as a lower frequency. And for low frequency, you can also go down with the VDD. Or other way around, if you go down with the VDD, your circuit becomes slower, so you have to slow down the frequency. And that helps to reduce this dynamic power consumption. Another option you have is that you do something like clock gating, so that you prevent effectively flip-flops from switching, yeah? If they are not needed. If a circuit is not needed, if a specific part of the design is not needed, you just switch it off from the clock, yeah? So that nothing can toggle. Okay, questions to that? Then one last thing that I need to mention, because I'm hardware security guy. So what is for us also important are things like the security of a circuit. We do not talk about this here in the lecture, but one problem we have is that we have this dynamic power consumption. Our circuit switches. If our circuit switches, if the bits flip, then we have a current flowing here, yeah? And we can measure effectively here the power consumption at the VDD or from an EM emanation. Yeah? So because if you have a current flowing here, you remember probably right-hand side rule from physics. Yeah? So if there's current flowing in, you get an EM field, and you can measure this with a coil. Yeah? So of course, for one single gate, hard to resolve, but in principle, already here doable. In practice, we do this on flip-flops, so works. The problem now is, if you implement in hardware some secure circuit, yeah, for instance, some, don't know if you heard of this, some AES circuit that is there for some encryption stuff, then an attacker can observe this, and if your switching activity depends on your secret key, the attacker can derive the secret key from just observing what the power consumption is. This has to be done usually many times. You have to do a lot of measurements and so on. You have to perform hypotheses and whatever, so there's a lot of math behind that. But at the end, it boils down to you have a switching activity and you can observe what is computed on chip. So, in order to protect against this, there are strategies like masking, hiding, and so on. So different modifications you can make to your circuit, special kinds of implementations to get rid of this. This comes on top if you really want to go behind what is pure digital design. So you have also to implement stuff like that. On top, we have things like fault detection attacks. So for instance, you go with a laser and shoot from the backside onto the chip. Then you can flip here bits on the internal nodes because you induce an additional current here, or here. That can change here the value. And at the end, the algorithm computes something wrong. Now you may say, okay, if a crypto algorithm computes something wrong, who cares? At the end, there's some cipher. But the problem is that you can, from the difference between what is the correct cipher text and what the wrong cipher text is, you may learn something. Okay, that was more like a side note I wanted to make. Questions here? No. Good. Do we need 5 minutes break? Huh? Do you need 5 minutes break? Yes? No? 5 minutes? Huh? Then maybe make 5 minutes break and then we continue. Yeah?
minus t setup.
Yes.
Why did you minus?
Why this is minus? So, okay. What we want is... Is it muted now? No.
I have a question regarding the ASIC and FPGA, right? This is regarding the...
Let us continue. So, now the next topic I want to talk about is memory elements. And yes, there will be two parts. The one is about the flip-flops, the other one is more or less about memory, I would say. Good. Okay. Let's start other way around. Which kinds of memories or memory elements in a circuit are you actually aware of? Anyone an idea? So what kind of memory elements did you hear of until now? RAM? Huh? ROM? DRAM? SRAM? ROM? VRAM is usually implemented as an SRAM. Well, what I'm missing is latches and flip-flops, which are also kind of memory elements. So all of this we can use to store data on a chip. All of them have a different purpose. So we start with SRAM. Did you already learn about SRAM at some lecture? Probably not, but not that I explain things twice. So what do we have here? Well, if you remember from what we had yesterday with the circuits, then we had drawn an inverter, right? The inverter, I just mark it here directly. Yeah, this here is nothing else than inverter, right? So we have one inverter here. We have the same structure here, so we have another inverter here. The output of this one goes to the input of that one. The output of this one goes to the input of this one, right? So if we have here a 0, this is forced to a 1, and it will keep the value. If this is a 1, this is forced to a 0, and it will keep the value. Now what comes on top? We have here and here an NMOS transistor, which we can consider just a switch. So if we want to write something to the cell, we close the switch, write our value into this cross-coupled inverters here, and open the switch again. And the chip will keep the value. As long as we have here power supply, nothing will change. If we want to read, I start first with the theoretical part. We close the window, close the switch. When the switch is closed, we can access the internal nodes and we can read, right? So from a high-level perspective, that is, I think, pretty clear what happens here. Now, it is, or the difficult part, I would say, is that we need at the same time to be able to read and write these nodes to read and to write these nodes. So writing, putting here maybe on this here a 0, on this here a 1. So on one VDD, on the other ground. Closing the switches, that will force here some value. But now we have only these two wires, bitline, bitline inverse, and want to read. Now how should we initialize these values? 0, 0 is one choice we can make. What will happen if we put it to 0, 0? It is okay, yeah? So it's one valid answer. So we have on a, maybe I draw it on the slide, then can I on this thing, then I can better later scan it. So we have the structure on the slide, yeah? And we have the nodes A and B, and we have the node bitline, bitline inverse, right? We said if we want to write, let's say we want to write a 0, we set the bitline to 0, bitline inverse to 1. We set, maybe I should add here, the word line to 1. Well, let's first start with shortly 0 and then it goes up to 1, something like this. So the internal node, whatever they are before, yeah, we just don't know. At the moment we set the word line, it should go up here, or it should be here at 0, here at 1, right? Then we can remove our word line signal. We can change our bitline, bitline inverse. Everything is fine because the word line here is disabled, so this here is actually a write. Now the proposal was for read to put this word line at this bitline and bitline bar both to 0. So what happens if I now enable the word line? Bitline bar is the right side. Huh? Well, this is just because you propose to put it too low, yeah? for reading. Yeah? I just put it too low. It doesn't really matter what happens here because we had removed the word line. So this is discoupled from the outside world, whatever is in the internal thing. So this is stored. Yeah? That was what I said. You can just actually now toggle the bitline bar. Doesn't matter. The question is, what happens to the internal state if I now, with bitline bar forced to 0, enable the word line? So the idea is, or that what was envisioned was that we read out our internal state, right? So before we had a driver here from external, well, so somewhere some input forcing this bit here to 1 and 0, but now we have externally 2 times a 0 and expect that now this internal node drives the outer world, right? So we change actually the role. Now if we drive this both to ground, it would work, yeah, you can do this, yeah? But from a logic perspective, on a first glance, both internal nodes would be set to 0, right? Then you disable the word line and you have some random state inside, right? So you have some, theoretically you have some oscillation, but this oscillation in practice will end at some point and you will fall in one of the two possible states, 1, 0 or 0, 1, right? Can you repeat please? So if you put both to 0,
Yeah, will be.
at least if you have a driver at the bitline and bitline bar, it should go to 0. Huh? So what actually happens? So I correct this, our preloading you can do with 0. I correct our preloading, you can also do with VDD by the way. I corrected a little bit. What you in practice do is you set it to VDD half. So we set it here somewhere in the middle, both sides. Huh? Now we enable the word line. Huh? So what happens now? A is on a different level, VDD level, or differently charged compared to bitline, yeah? But it's connected to bitline. So what will happen is that A goes a little bit up. Probably I use another color to make this better visible. So this here goes a little bit up to VDD half. The bitline will, because A is 0, go a tiny little bit to 0. Not fully. Because you have, or you can envision this as, I just draw maybe A. This goes to the bit line, right? We have, this here was, or I should, well, there's this, we make it like this, so there's a switch, yeah? Because that's the transistor which is there, that's just a switch. We use here effectively, we have, I draw it like this, node B, yeah? And this here is connected to here, yeah? And there is effectively, no, I did something wrong, sorry. Sorry, it was, this here should be removed, I think. This one here is connected to the, now it gets, sorry, I redraw it. That was not a good way. So we have this one here is our inverter that we want to consider. And the node A goes here where I switch to the bit line. Here is this input is connected to the output of the B inverter, right? And the input of this inverter is connected here, right? Then this here is node B, and here we have node A, and we only consider node A. Yes? So, good. Now, what happens if we have, or on an analog level, we have here a large capacitance. We have here some small driver. So effectively, this node here provides some charges to the capacitance, or the other way around. That causes that this node here goes down. So, or in our case, it goes up towards VDD. So the voltage, we have here a straight connection, so the voltage should be the same. And if the driver is not super strong, and we have a lot of charges on the capacitor, then it will roughly go up to VDD, or VDD half in that case. Okay? If we have this on the same on the other side, the same happens to B. So on B, it's the other way around. Bit line inverse is slightly increased. B is slightly decreased. So I can also try to draw it here once. So we have effectively, we have here VDD half. We have here VDD half now for reading. We have here internally, we have the, here I just write a logic 0. Here we have a logic 1 on the other side. If we now close here, the electrons from here should go into the bit line. But at the same time, since this is not an immediate process, the voltage here is increased. Increasing the voltage here means this one here should flip, right? So this here starts to go into direction where it starts flipping. In parallel, we supply VDD here. So the charges here, electrons should flow from bit line inverse into this node. Means this inverter here starts switching. So at the end, if this here is large enough, at the end everything should be at VDD half, and we have here only a connect, just resistors. That is what we would expect if we drive here VDD half, and somehow we need to drive it, and have here current 1. And if we preload, so if we have here, what we do is actually we preload here with a large capacitance. If we preload this large enough, then we will first put this towards VDD half, put this here, same effect towards VDD half. And then, depending on how the internal structure is and so on, this will either flip to 1 or 0. Huh? Because you have an inverter, it should go at some point in a stable state, but if you wait for long enough. Huh? Now, to ensure that that does not happen, you have at bitline inverse. This is connected, I just draw it like this, to some sense amplifier. The purpose of a sense amplifier is that a small delta V is translated into a large delta V dash, which is actually then 0, 1 or 1, 0. So either we have here, well, let's maybe better write VDD 0 and 0 VDD on an analog world. This one here, this circuit, is built in a way so that whatever you have here is also here at the input. So you can envision this like you have here some feedback. In practice, it looks very similar to what you have for the SRAM cell, but with different transistor sizing. So it's much stronger driver. So what you see then is that this sense amplifier effectively sees a small voltage drop here. I'll take another color. A small voltage drop here in the bit line and bit line bar, compares this and amplifies it up to the full level. So I write here sense amplifier. This causes that we also refresh effectively our B and our A. And then we have effectively here the values you want to have everywhere, and we can disable our word line and are done. So this is effectively the read process. So on a high level, you can say, okay, we just read it out. Perfectly fine from a logic perspective. Why do I go into this detail? This detail tells us that if we have only such a cell, we cannot operate it. We need additional infrastructure for reading and writing the cell, which is analog design, which is usually comparably large. And this is, well, the visualization of that is shown a little bit here, once more. And this is why you try to share this additional read and write circuit. I just need to remove maybe the stuff from the table. So, what can we learn from that? We know we have a memory cell that consists of 6 transistors, pretty small. We know that on top of this, we need a read-write circuit, which has quite some overhead. On top of that, usually you have a register bank for read-write to have the thing synchronized. So overall, you have a lot of interface overhead in order to access the single SRAM cells. And this is why it makes only sense to have, if we share these interfaces. So we have an array then of SRAM cells. We can connect the bit line bar to one common sense amplifier that is again connected to one register bank. And then we can write and read all of the cells with the same infrastructure. If we make this, then, well, the larger actually the SRAM block is, the more efficiently we can share this. So a large SRAM block makes sense. A small SRAM block has a lot of overhead in sense of we have additional registers, we have additional control logic, we have additional read-write circuit. Good. Nevertheless, it's a relatively fast circuit. It keeps its value as long as it's applied, and is, for large memory size, is the way to go on most of the chips. So, for instance, if you think about the chips in your smartphone, on these chips, the cache for your controllers is built as an SRAM. Yes.
So is that
Yeah, that's just unknown.
Okay.
Yeah. Okay. Now, this is a little bit the side note for the FPGA. So for the FPGA, we have these block RAMs, which is just classical SRAM with a specific interface, but at the end it's just classical SRAM. This is quite area efficient. That are dedicated building blocks that are quite small. It is synchronous read-write, so we can write with a rising edge, falling edge onto it, read with rising and falling edge to it. And it's, in most of the cases, the best choice. There's another implementation with this distributed RAM. That is actually the memory used for the configuration of the lookup tables reused. That is more flexible in placement because everywhere where you have a LUT, you have such an SRAM block. Or at least for a few of them. So it's not a central place where you have this block RAM on your FPGA. But you can effectively, everywhere where you have logic, you can also put a small memory. That makes the path from the memory to your logic shorter, which is a benefit. The second thing is, this is still, in the way it's implemented in current FPGAs, still a synchronous write. So you write with a rising edge. But you can have an asynchronous read. So meaning that as soon as you have the write operation done, the result propagates to the output without any clock cycle in between what you have for a fully synchronous read-write. So for a fully synchronous read-write, you have one clock cycle where you can write, and only on the next rising edge you can read the same data. For this synchronous write, asynchronous read, you can write in one clock cycle and immediately use the written data, which is sometimes a benefit because it can save your clock cycle. Okay, so if SRAM is the way to go for our on-chip, why do we need something else? Why do we need flip-flops, DRAM, ROM, whatsoever? So the processing speed, we will go for the SRAM or maybe for the flip-flops. Flip-flops usually require more area. So flip-flops are more than only 6 transistors, meaning your area increases. If you have a lot of cells, if a lot of memory, you would go for an SRAM. If you have only few memory elements needed, you would go for flip-flops. So, the other part, what you said, is DRAM and ROM are used for other kinds. You have the next lecture, right? Yeah, good. Then we continue at that point tomorrow. Yeah? See you then.
Both BL and bar can go the same together.
Can you repeat, please?
BL and bar BL can go 0, 0 and 1, 1 together. Cannot what? I thought if BL then BL bar must be the opposite.
So, effectively, then what I wanted to say here is they can have here any value because we do not enable the write.
These are enable.
So the write enable should be B. So the write enable that we have on the slides, or write line. That was write line. I think I just they should have the same abbreviations on the slides. Yeah. So the right line effectively is, if this is 0, the connection here is closed, and you can apply to BL and BL bar whatever you want.
Cannot apply, okay. Cannot apply.
You can apply whatever you want. Yeah? So it doesn't change the internal
So
state.
when this is 1, you overwrite these two.
If this is 1,
You overwrite, it doesn't matter. these two.
you may overwrite these 2. Yeah.
Tomorrow go through again. Tomorrow I ask again. Tomorrow go through, now no time already.
Yeah.
Okay.
For
So-
the AC